Okay, so in our last lecture we dealt with the theorem of Menelaus, and I made a big deal out of the basic fact that it's a two-sided theorem. So there's a numerical relationship which says that if that relationship holds, then 3 points are collinear, and it can go backwards. If 3 points are collinear, then that numerical relation holds. So it's an if and only if statement, which is as you know in mathematics, it's a big deal. Now I would like to give an example. In this example, we shall have occasion to observe how strongly such a property can become apparent in applications, can be useful in applications. Okay, so the thing I would like to talk about is the so-called Newton line. So that's my second application. So application number 2. So my first application was in my last lecture. It was a rather standard classical and rather boring, I should say, result. So the second example. Now this is referred to as the Newton line. The Newton line. So it's a geometric property which is ascribed to attributed to Newton, the Newton line, and it has got a very beautiful, short, concise expression expression in the older geometric language. Let me do it first and observe the effect later, and do the explanation even later. It says, in a complete quadrilateral, the midpoints of diagonal segments. Let me say just diagonals are collinear. The portent of such a one-liner, although I've written it two-liner, never mind. Portent of such a one-liner should have been obvious to a person, let's say 50, 60 years ago. Nowadays it can be a little bit difficult to understand what's going on. So there are certain expressions we are not familiar with. So what's a complete quadrilateral? Well, if I ask you what a quadrilateral is, you would possibly struggle with something like, let's take 4 lines, okay? Something like this. Let's take, so let me explain this. What's a complete quadrilateral? So you take 4 lines, you would say, I take 4 lines, and then well, that's about it. Perhaps you would even say, well, the 4 line segments following one another, forming a closed whatever, closed curve, closed broken line, and the region that such a broken line, such a polygon encircles, etc., etc. Now, as you can see, these are all rather troublesome things, and you have to do a lot of hand waving, so on and so forth. In what people called 50 years ago, I mean 60, 80 years ago, what people called modern geometry, which is a funny thing. I mean, you should be well warned not to call anything modern. Okay, it's funny because things which are up to date have a very funny way of going very fast out of date. Okay, so this was 80 years ago, modern geometry. When people talked about modern geometry, they rather restricted their attention to lines and points, and they did not want to talk about line segments, order relations, so on and so forth. Anyhow, so when you say a quadrilateral, you may say quadrilateral, four lateral side, four-sided. So I take four lines. That's excellent. So where are the vertices then? Well, you might think that's an easy question to answer, and you might say, well, here are the vertices. I've got these four lines. I let them intersect 2 by 2, such as this, such as this, such as this, such as this. And these are the vertices. But you see, that won't do. If you've got four lines, and if you let them intersect 2 by 2, the number of intersections is in general 6. You see? For instance, you must also take this point into account, mustn't you? And you must also take this point into account, mustn't you? So, when you say a quadrilateral in modern geometry, modern in the sense of 80 years ago, okay? In the sense of modern geometry, you must say, well, 6 straight lines. And we of course understand that to be in general position. No 3 of them are concurrent or something, okay? So you don't have that sort of thing, or parallel. So you get something of this type. Okay, so 4 lines. And the vertices are the 6 points. They are all vertices. There is perfect democracy. You can't say, I'll take this vertex, but the other vertex is for some reason or another unsympathetic to me, and I'm not taking it. Okay? Just to reduce the number of vertices to your traditional 4. No, you can't do that. You have to take all 6. Okay? So that's why this thing is called a complete quadrilateral. And what are diagonals? Now let's suppose you are working with the naive things and you have forgotten these 2 points. And where would your diagonals be? Your diagonals would be, of course, well, this line. I mean, I'm considering line segments, by the way, as line. I'm considering diagonals as line segments, by the way. So it would be the line segment joining these 2 vertices. And what's so interesting about this? You see, if you join these 2 vertices, then what you will get is a line which is a side already described. So you are joining 2 points which are not already joined by a side. So you are joining, in fact, 2 points which are not adjacent. They are not neighbors. These 2 points are neighbors because they are on the same line. These 2 points are neighbors because they are on the same line. So you are joining points which are not on the same line, which are not adjacent points. Good. And of course you're doing this. So these are your diagonals. I'm just drawing them as segments. Well, that would have been fine for your preliminary school kind of geometry. Okay? But if you want to see what happens on a complete quadrilateral, then you must also go to the remaining 2 points. Let me complete the picture. I'm not quite sure if we are able to film this whole blackboard. Okay, so you see, now what was the diagonal? The diagonal was the line segment that joins 2 non-adjacent points, 2 non-neighboring points. So I've got 2 here, non-neighboring, 2 here, non-neighboring. Is that all? Well, these 2 are neighbors because they're on the same line. These 2 are neighbors because they are on the same line. These two, they are all on the same line. Well, these 2, they are not on the same line. They are in fact, the line segment that joins them is also a diagonal. Here it is. That's it, Cheshire. That's your complete quadrilateral. A complete quadrilateral is 4 straight lines in general position. That's to say, no 3 of them are collinear, they are not parallel, so that They intersect in 6 points. They're called the vertices. And you join non-adjacent pairs of vertices 2 by 2 to obtain line segments and call them diagonals. So what does our theorem tell us? The theorem says that in a complete quadrilateral, the midpoints of diagonals are called this. So I take the midpoint of this diagonal, I take the midpoint of this diagonal, and I take the midpoint of this diagonal. They are. Treat that well. You know. So they are, according to Newton, they are supposed to lie on the same line. Right? The proof? Here it is. So I've explained the content of the theorem. And by the way, I really would like you to notice the way the English language assumes an older, yet more quaint and very effective form. Okay, so if you go backwards about a century or so, it's got its own terminology which makes life easier. Things like complete quadrilateral. So you can say things in a single line, which is rather beautiful. It's rather like the Ottoman Turkish. You can say things so fast, so precise, but well, the words are just too old. But that happens. Right. Okay. So the proof. Okay, so I would like to draw a larger diagram. The proof. So let me draw a new diagram. Okay, so the way I like to draw it is as follows. There it is. So I want a rather biggish configuration. Well, it's always a question whether a proof is elegant, whether a proof is transparent. You learn a proof and you are satisfied that the theorem is true, yet somehow you may be left unsatisfied as to the origins of the idea, so where it all comes from. So occasionally the mathematician has to say that, well, this proof is elegant, but it's not transparent. And some proofs are natural, it's just follow the statement of the theorem, and somehow the proof falls out somewhere. Well, all these are very beautiful, very good virtues for a theorem, for a proof to possess. Yet, in teaching mathematics, sometimes you care neither for transparency, nor for elegance, nor for being natural. Because you see, for instance, in this case, what I'm trying to do is to illustrate the power of a technique. Why is it so important to have something like theorem of Menelaus in your arsenal, and how it can be used? As you remember, I have made a big deal out of the fact that it is an if and only if statement. In fact, in this proof, I shall use Menelaus' theorem in both directions, and I shall make a big deal of illustration, showing it off. Right. Okay. So, this is not. By the way, this is not a terribly ugly proof or something. Okay. So here is your. Anyway, here is your. This is not an ugly proof or something. But I mean, you may argue back and forth. That's all a matter of taste. So here's our complete quadrilateral. So the 4 lines and the six vertices A, B, C, D, E, F. Okay, so Right. And the diagonals. The diagonals are, of course, the diagonal joining the non-adjacent diagonals AC and BD. And it's not easy to get a good configuration. And EF. So I'm being very careful, but you know, you don't always get a very good picture. Pictures are good in many different ways. Of course, they may appeal to you by their proportions, so on and so forth. But there are certain proportions which are optically not only more pleasing, but they're also telling, you know. They just appeal to your intellect. So there we are. Let me see if I've got it all right. Okay, so the midpoints of the diagonals, let me call them K, the midpoint of the line segment AC, L, the midpoint of the line segment BD, and M, finally, the midpoint of the line segment EF. Good. Okay, so I shall prove that these red dots are in fact coordinate. They lie on the same line. Okay. Now, here comes one point where the proof is not quite natural. So I'm pulling something out of my sleeve. Well, for the experienced person in geometry, this is not wholly unexpected, because you see, I have promised to use the theorem of Menelaus to prove that these red dots, K, L, and M, are on a straight line. Well, of course, the question is, you know, to be able to make use of the theorem of Menelaus, there must be a triangle in the first place. There must be a triangle, and your K, L, and M must be on 3 respective sides, so that you can look at the ratios and do some computation. That triangle is not there. Let me now introduce that triangle by, well, if you wish, rather unnatural means. I do it as follows. I take the midpoint of AB, call it U. I take the midpoint of AF, right? Call it T. So it goes TU, okay? And then let me take the midpoint of F. Okay, no. Let me take the midpoint of BF somewhere here. Let me call it S. Okay, so I've got this blue triangle. Now look at it. STU. Okay, so let STU. I am not drawing the whole thing, but you may already have noticed certain things. Okay, right. U is midpoint of AB. T is midpoint of AF. Once again, I mean, this lecture seems to me just a tribute, just a complete big tribute, a big homage to this theorem of Thales about parallel lines separating, okay, respective proportions which have to be equal. Look here, that's the midpoint of AB. That's the midpoint of AF. Join them. It must go through the midpoint of AC, which is? Great. Take the midpoint of FB, which is S. Take the midpoint of BA, which is U. Join them. It must go through the midpoint of BD, which is? L. Great, great. And finally, take the take the midpoint of FA, which is T. Take the midpoint of FB, which is S. Join them, and it must go through the midpoint of FE, which is M. There we are, çocuklar. We have got the triangle. Here's the triangle. And our 3 points, red points, K, L, M, on the respective sides of the triangle. So we may
start applying the theorem of Menelaus. What time is it? Yeah. Well, to apply the theorem of Menelaus, of course, you must, okay, so I shall have to work out, okay, so the track, okay, Menelaus in K, I'm sorry, S, T, U. I will try to do this, okay? I like to put my exclamation mark in front of the thing, like the Spanish people, you know. So the thing is coming. So, I have to work out, so STU, so KT to KU, so I must work out KT, KU, and I must multiply it with LU. Now, do you notice the extraordinary advantages I have obtained by using the cyclic way of writing things down? K2U LS, and finally, I mean, I can write the thing blindfolded. I don't need to look at the diagram. MT. Okay, so will this or will it not turn out to be +1? Now let us see. What is çocuklar KT to KU? Clearly, this TU is parallel. Well, we have already talked about it. TU is parallel to FB. So you come to the conclusion that this ratio KT to KU must be exactly the same. KT to KU must be exactly the same as CF to CB. Are you with me, çocuklar? Again, this line is parallel to this line. UT joining the midpoints of AB and AF is parallel to BF. So it means that if you take the ratio, so KT to KU, it's exactly the same as CF to CB. Great. Now let's do something similar with LU, LS. What about this? LU by LS. Do I have something similar? Of course you have. L, U, S. The line SU, the line SU is parallel to FA. So if you take the ratio LU to LS, it's exactly the same as the ratio DA to DF. Are you with me, çocuklar? So it's going wonderfully. I'm just applying and reapplying, turning around and reapplying this basic theorem of Thales, which is possibly 3,000 years old. Okay, right. Let's try to apply the same thing to M. S, MT. Do I have something like that? ST. Well, of course I can, because ST being the line joining the midpoint S of FB to midpoint T of FA is parallel to the straight line AB, which means that the ratio of MS to MT is exactly the same as EB to EA. Okay, so let's put these all together. Okay, so so what can I say about this? What can I say about this quantity? Well, you see, do you remember our numerical formula? It was xa to xb, yc to ya. So in every quotient, the second letters refer to the triangle. Şunlara bir bakın. Just look at these two things. Just look at these. FB, AF, BA. So these actually refer to the triangle A, B, AFB. Okay? Now I must invite you now. I must now invite you to look at this triangle. Okay, so so this is the last step. So let me just disfigure everything by pointing out this triangle. Now, what's happening on this triangle? On this triangle, you are looking at the points C, D, E. Where are they? C is on the side BF, D is on the side FA, and finally, E is on the side AB. Moreover, these 3 points D, C, and E are on the same line. So now, I'm applying Menelaus theorem this way. Okay? So 3 points on respective sides are collinear. Hence, okay, this is equal to +1. Since D neydi? C, E are collinear. And I'm using Menelaus in ABF and Menelaus this way. So I'm starting from collinearity going to the numerical relationship. It finishes the whole thing. So this quantity is 1. So since this is equal to 1, I can go to the conclusion that K, L, M are collinear. How? Menelaus. In what triangle? In STU. Which direction? Backwards. From the numerical relation, I've come to the geometric property that the points K, L, M are in fact collinear. That's wonderful. I should say that's really a moment to cherish. Okay, so I think this example should be quite sufficient, quite sufficient to illustrate two things. It's important to work with directed quantities. So it's stupid to say, let's take the points KL, L inside, K outside, M again inside or something. That kind of concoction is really terribly stupid. I think it's the trademark of a person who is stupid, who is totally unsuitable for any kind of geometry. Okay, so if you go about saying, I have taken a triangle, I want to apply Menelaus, but one of the points must be outside, the other two is inside, so I take lengths, etc. That is just stupid. Just use directed signed quantities and you are home free. That's the first important thing. Second important thing is that this kind of thing is both ways, works both ways. So you can start with collinearity, end up with a numerical relation, just as we did in this case. And then you can start with a numerical relationship and end in collinearity. Okay, so that's really the power of this theorem. Okay, so this, by the way, we have been into a rather historical statements, and I think this is a very good point to stop.